Thank you. So this work was supported by National Science Foundation, and now I'm in National Science Foundation, and I have to declare that this work was done at University of Utah and has nothing to do with my work in National Science Foundation. So the motivation for this work is that these machine-brain interfaces are used in prosthetics and also in trying to map the circuitry of the brain. And right now, they are basically quite large. They're about centimeter square area, centimeter cube volume, centimeter cube area, and then they have centimeter square area, and they have about a centimeter in depth. And in order to implant them inside the body or inside the brain, they require a traumatic surgery, and in order to implant this inside the brain. And there is a paradigm shift to go. These arrays are, this is a Utah array that has been used for a long time now. And they have about 100 electrodes. And they usually record from one kind of region inside the brain. And I'm not showing all the electronics and the coils and stuff that are attached to this for telemetry. So you can imagine putting this inside the brain and securing it in somehow on the skull in order to do the reading of the neuron firings. It is quite a bit of work. And there is a paradigm shift from doing this kind of work, recording from 100 neurons or something on that order, going from there to about 1,000 neurons and scattered all around inside the brain. So if you want to do that with arrays like this, you need to implant these in different parts of the brain, and that is not practical simply, just because of the amount of volume they require. So one of the ways that one can address this issue is to go to electrode arrays on flexible substrates where you can fold these and possibly inject them using some kind of a hypodermic needle. So as the hypodermic needle only requires maybe millimeter square area to be drilled in the skull, so you can basically insert this and thank you, and inject the folded array into the brain matter and let it kind of unfold itself and launch itself in different regions inside the brain. So by doing this, you can go up to maybe a few hundreds of these, and each of them has maybe 4 to 10 electrodes. Then you can address 1,000 neurons that is needed by neurologists and people who are interested in looking at the brain circuit. We're not there yet, but the idea is kind of appealing. Now, in order to do this kind of things, what kind of technologies we need to bring on board? Well, if you have a flexible electrode arrays on something like PET or a variety of different substrates are available for this, we need to develop these coils possibly for communication. Electronic has to be kind of added to it. Maybe electrodes are not that much of a problem because they're patches of metals or some conducting materials, and one can do some kind of a nano texturing of the surface of their surface so that you give them large surface area in order to reduce their contact resistance to the neural tissue. But probably the most difficult thing to kind of develop is telemetry and wireless part of this, and how to power these in situ inside the brain. So in order to reduce the amount of power that you need to kind of excite these and read their output or the reading of the nearby neurons, one needs to develop extremely efficient electronics for transduction. So this work is basically part of that effort to come up with electronics that are extremely low power. By the way, this also brings all the MEMS resonators and filters and stuff on board, because MEMS resonators and filters are supposed to be extremely low power, and also they have certain amount of computation embedded in them. So this kind of schematically shows that we are going to, the objective is to put a large number of these, maybe 50 to 100 of these inside the brain, inject them using hypodermic needle, and launch them in different locations inside the brain. And what they need to do is they're going to be extracellularly detecting neuron firings, and that goes up to about 100 microvolts. That is as opposed to intracellular type of transduction where you have maybe 10 millivolts or 50 millivolts of voltage to sense. So you need about 5,000 amplification in order to take signals from this level and transmit it to the outside world. So there are some other things that needs to be developed as well. So if this is, let's say, one of those little coils inside the brain, then one needs to come up with techniques to amplify the signal. And there are these near-field approaches that people have been working on for the past 5-6 years. And we have also started adding that. So what I'm going to do is talk about this tunnel diode circuit, which we have discovered to be very low power in terms of taking the signal and then producing a high-frequency signal that can be transmitted to the outside world. So actually, before I kind of discuss the circuit itself, I would like to mention to you that since it is difficult to get neurons and kind of maintain them inside the lab, you have a dry lab, we have come up with a way of using just coaxial cables and putting some waxes in the at the output of the coaxial cable and generating signals that are very similar to what you get out of neurons. So we have basically made our own kind of artificial neurons for as far as electrical properties are concerned and generating the signals that we need to detect it with our circuit. So the circuit that we have been working on is kind of schematically shown in there. It is a very simple circuit. These circuits have been around for a long time, and it relies on and off kind of properties of this tunnel diode. These diodes are also called Ezaki diodes, and they're based on the old versions of these are based on P plus N plus regions. And their ID is, unfortunately, I don't have it in here, but it shows kind of a very rapid rise, and then it goes down and it goes up as a function of voltage. So in the initial stage, it is on, and then it becomes off. So it switches between on and off states. So every time that kind of turns on and off, it kicks in a certain amount of energy into the loop, and it sustains the oscillation of the oscillator. So why is it so low power? Well, the current going through the tunnel diode is proportional to the area of the diode. So by reducing that area, we can reduce the current. And the voltage, the turn-on voltage, depends on the materials that we have and the doping levels that we have inside diodes. So depending on what material you use, in the case of germanium, the turn-on voltage can be around 0.2 volts. When you go to silicon, it is 0.5 to 0.6 volts. So by changing the material, you can change the voltage. So voltage and current can be changed independently. So that's a great thing about this. And it is kind of a voltage-dependent switch. So in order to make this work at very low power, we use a germanium diode for biasing the circuit. And the Q values are pretty high for a simple circuit like this. And this is the actual voltage that's applied across this, this circuit. And you can see the center frequency of this oscillator that is formed by the loop depends on the voltage that we are applying. So this is the key thing that we use for transducing the voltage coming out of the neurons. So if you take, let's say, 10 microvolt and amplify it to the levels where you can input into this circuit is going to basically produce an output whenever there is a neuron that is nearby and firing. So, so that's basically the idea, and the sensitivity that we have obtained for typical germanium Ezaki diodes or tunnel diodes are on the order of 4.19 hertz per millivolt. And the quality factors are pretty high. They are, before I leave this, I would like to mention that right now we are using this quartz crystal as our oscillator, but our plan is to replace these with MEMS oscillators. And by going to the MEMS oscillators, therefore we can have a bank of these. And then each of those injectable electrode arrays that we put inside the brain will have a slightly different frequency, so we can do frequency multiplexing for our transduction. This shows some of the traces that you get. So if this is the neuron firing, it's amplified version of the neuron firing. The frequency that is generated by the oscillator is shown in there. This can be used in the echo mode, so you can send an RF signal power the circuit, and then make it wait for a neuron firing event, and then the output will reflect the frequency that's proportional to voltage that's applied by the neuron firing. And it works quite well. So I would like to go back to this kind of idea thing that I put in there. So the coils work well. In order to make them kind of interface with the brain, we have to put other coils on the surface of the skull to kind of generate near-field conditions for amplifying the signal for powering purposes and also for reading the frequencies coming out of each of these. The substrate is not a problem. Powering is something that we still need to work with onboard supercapacitors so that we can store a certain amount of power onto these. And we are just about to go to kind of rat testing these things inside rat brain and see if they work in actual animals in vivo. Now, I kind of thought to put this in there to show you how this unfolding of the array works. This is the complete array. This is where the coil is, and the electrodes are kind of scattered all along the axis of this array. This particular one has about 10. And we fold this and hold it together using sugar. So when sugar dries up, it gives you exoskeleton. It kind of makes this a little bit stiff. And then it can be injected using the hypodermic needle. This kind of shows as it comes out of the hypodermic needle. And most of these are done inside the gel, and we have experimented these in sheep brain and a bunch of other biological medium, agarose gel. But this is basically typically what you get. So after they're launched into the medium that has lots of water typically in it, the sugar starts dissolving, and the kind of array starts unfolding itself. And as it unfolds, our guess is that these branches that kind of each of them have a bunch of electrodes on them, they basically take the least resistive path and find kind of sweet spots near the neurons. So if you kind of imagine that neurons are granular structures, they are going to try to unfold themselves through the crevices of these neurons and find the sweet spot near particular neurons that they are going to transduce. So kind of shows, I have a couple of video clips that show exactly how they unfold themselves and how they launch their branch structures near different granular structures. So in conclusion, it's kind of a new concept in electrode arrays. So instead of performing surgery and attaching these electrodes array into the brain, why not kind of make them injectable so they can be injected inside the brain and they go there and unfold themselves. Now, in order to be able to do that, we have to make everything flexible and very small. So the supercapacitor has to be made small. The electronics has to be made extremely small and high efficiency and low power. And the electrodes need to be nanotextured so that they have very small contact resistance with the neuron matter. So that has to be on the order of a few kiloohms. And when you go to 50 by 50 micron type of electrode arrays we are looking at, if you have a glassy platinum or metal, then the contact resistance is on the order of 10 kiloohms to about a megaohm. So nanotexturing helps there. So with that, I will see if there are any questions. Thank you.